Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Classification and marketing. Basically, before a packet can have a QoS policy applied to it, the packet has to be classified. Again, we can have X amount of numbers of classifications that are user defined. The classification will determine the class of traffic to which that frame belongs. Only after traffic is marked can a policy be applied to it. Is it marked voice? Is it marked real time? Is it marked low priority? That's what it means by marking. So how a packet is classified will depend on the implementation. So methods for classifying traffic flow for both layer 3 and layer 2 could include things like interfaces, ACLs, and class maps. Traffic can also be classified layers 4 through 7 using the network-based application recognition, or NBAR. It all depends on the type of router that you have set up and the features that are there for QoS. So the traffic will be marked, usually depending on the technology that is in use. The decision of whether to mark traffic in layer 2 or layer 3 is not trivial and should be made after considering the several key points. Layer 2, marking of a frame, performance for non-IP traffic. And that means QoS options are only going to be looking at the frame. Where if you're doing layer 3, marking will carry out the QoS information end-to-end and be looking specifically at layer 3 data. So QoS tool, like in 802.1q, that's going to be looking at layer 2. It's going to be dealing with the class of service, the COS. If we are dealing with 802.11, that's also layer 2. That's going to be using its wireless traffic identifier, the TID. If we're looking at MPLS, that's going to be the experimental. If we're looking at IPv4 or IPv6, that's all going to be done at layer 3, and that's going to be looking at the IP precedence, the IPP, or differentiated service code points, the DSCPs. Interesting part here with the DSCPs, that does require more bits for our QoS function. So let's go ahead, let's look at this a little bit more in depth. With our QoS tool for our 802.1q, you will see that we have a TP-ID, which sets a priority, a CFI, and a VLAN ID. Well, the priority is actually the 3 bits used for our QoS. Sorry, our class of service, not our QoS, but our COS. That COS is part of the QoS features at this layer. So what are some of the COS values? Well, there's 8 bits options, so there are 0 through 7. And again, best effort, medium, high priority, call signaling, video conferencing, voice bearing, or reserved options. These allow us to flag that bit accordingly. If we're doing marking at layer 3, for example, we are looking at the type of service. If we're looking at an IPv6 header, it's still traffic class, but it's still essentially the same as type of service. With the types of service and traffic classes, basically the carrying packet marking as assigned by the QoS classification. This is done through the differentiated service code point, the DSCP field. These 6 bits will offer a maximum of 64 possible classes. So when we're looking at classes, we can have the different classes set up, and you can define what types of classes. There are 64 possible classes. The remaining 2 bits are called the IP Extended Congestion Notification, ECN bits, and they can only be used by ECN-aware routers, and this allows marking of packets instead of dropping them. Again, way outside the scope of CCNA, but this is just background of understanding QoS and how we should prioritize traffic and the functions of prioritization. So the DSCP values, there are 64 DSCP values. best effort, expedited forwarding, or EF, and essentially that's going to be a DSCP decimal value of 46 or binary value of 10111003. The first 3 bits map directly to the layer 2 QOS value, and the other remaining 5 are used for voice traffic. At layer 3, Cisco would recommend the EF only be used to mark voice packets for now. There's also the assured forwarding section, AF, and this will define the use of the 5 most significant DSCP bits to indicate query instead of drop preferences. So if we're looking at these, here we have our classes, and then we have our drops, our low drops, medium drops, and high drops. And we can record them based off of classes and assured forwarding values. So the assured forwarding values are shown in the figure. The AFXY formula is specified as following. The first 3 most significant bits are used to designate the class. If it's class 4, the best query, and class 1 is the worst query. So class 4 is going to be the best option. The 4th and 5th most significant bits are going to be used to designate the drop preference, while the 6th bit is going to be set to 0. Let me grab my pen. So again, class, is this class 1, 2, 3, or 4? And then we have our drop preference, and then the last one will just be set to a straight 0. That way we can define which class we are going to be put in, class 4 being the highest, and which drop category we're going to be in. Low drop, medium drop, high drop. So for our class selector bits, also known as CS bits, the 3 most significant bits of the DSCP field and indicate the individual class. We already knew that from the previous slide. These will map directly to the 3 bits of the QoS field in the IPP field to maintain the compatibility with 802.1p as well as RFC 791. Again, way more depth than you actually need to know. This was more of a just understanding the background of how QoS functions and understanding that there is a very specific standard set to be used. We also have what's called a trust boundary. Our trust boundaries should be classified and marked as close to the source technically as possible or as feasible. These will define the trust boundaries. Basically, trusted endpoints, secured endpoints, and traffic can also be marked at the appropriate layer 3 switches or router level. That way, we can understand the type of traffic coming in, and we can trust what they are. So, we need to back up a few. We have to talk about congestion avoidance. Congestion avoidance tools, we've already talked about some of the preemptive tools. Basically, this allows us to monitor network traffic load in an effort to anticipate the congestion to avoid them. They'll monitor the network load in an effort to anticipate, maybe avoid the congestion. They will basically perform some form of bottlenecking before it becomes a problem. They will monitor the average depth of the queues in use, and when the queues are below the minimum threshold, they start dropping packets. As these queues fill up the maximum threshold, a small percentage of packets will be dropped. They can filter all of this before they are dropped, before they are reaching that device. They do that through the WRED. This will allow for the congestion avoidance function to kick in. The WRED helps avoid tail drops and maximize network performance, and really utilize TCP-based applications and improve that performance. Again, with TCP, it's connection-oriented, so when a TCP packet is dropped, an acknowledgement is not received, so it will generate more traffic. But it's more about controlling when the packets are dropped. That way we can funnel or bottleneck them before they get to a device that is really slammed with its resources. One of the last major sections are shaping and policies. Because again, traffic can be all over the place. if we're shaping the traffic, we can get a nice steady stream of traffic, and that's the point of our shaping. So the traffic shaping will retain excess packets in a queue and then schedule the excess for later transmission over an increment of time. This allows us to have a smooth packet output. Shaping is an outbound concept, and again, all it really does is it starts queuing the packets so that we can have a smooth signal being sent. Policy is applied to the inbound traffic on an interface, so policing is commonly implemented by service providers to enforce a contracted information rate, or a CIR. However, the service provider may also allow bursting over that speed. If you ever wonder why when you get like 100 megabit speed and you do a speed test, you get 150. Well, those are burst speeds. You can get a little bit above what you're paying for. However, when you look at the data transmission rate over a given period of time, it should be averaging out to what you are paying for. Sometimes it can burst above, sometimes it's below, but on average it's staying the same. So when we're looking at our policy guidelines, essentially we must consider the full path source to destination that we control. A few guidelines basically enable queuing at every device in the path, classify and mark traffic as close to the source as possible, and shape and policy traffic flows as close to their source as possible. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.